Greetings, everybody. I posted a second practice problem involving Newton's second law as applied to what we call an inclined plane problem. And here's the problem itself. Um, you've got a crate whose mass is 225 kilograms, and it's being pulled down an incline. Uh, it's being pushed and pulled down an incline. The incline is 20 degrees, meaning that's what theta is. And it's being pushed and pulled by two forces. A horizontal pushing force, P. Again, P is in the original negative x direction. See, it's parallel to the ground, not the incline. And then a pulling force, a tension force, we'll call T, and 400 newtons. And this force makes an angle of phi, and it makes an angle of phi equal to 35 degrees, as indicated here, with the incline. Notice the angle phi is the angle between the pulling force T and the incline, because that dotted line is clearly parallel to the incline. All right, and again, I want to find the coefficient of kinetic friction, UK, between the crate and the incline. So again, I know the mass of the crate, I know the angle theta, I know the magnitude of both forces, P and T, and I know that the tension force makes an angle of phi with respect to the incline. Well, now, we don't want to overthink it. We're going to draw in, remember, on the crate, we're going to draw all the forces acting on the crate. And then remember, inclined plane, our x and y axes are defined by the incline and perpendicular to the incline. So, and just as we resolve mg into its components, we're going to have to resolve the pushing force P into its components. And just a third thing, we're going to have to resolve the pulling force T into its components. But not a big deal because we know all the angles. Let's go ahead and let's bring up the solution. And the first thing you want to do is always, before you do anything, draw all the forces. Then use basic trig to get the components. Then apply Newton's second law in the x direction and apply Newton's second law in the y direction. So that's always the rubric. First, draw all your forces. That's step one. Step two, do all the resolving into components. That's step two. Step three, apply Newton's second law in both the x direction and the y direction. Step four, do the basic algebra to solve for the unknown quantity. In this case, we want UK. Now remember, this problem stated that the incline is being pulled and pushed down the incline at a constant speed. So meaning V is constant. Again, this arrow means, hey you all, the object is sliding down the incline. That's going to represent the positive x direction. And V equal to constant means that A is 0. Now let's go ahead and do all the forces. Okay, well, here's the crate. The pulling force T and the pushing force P were given in the original problem. They're already drawn in, but I redrew them, of course. Okay, but remember we have mg, we've got fk, we've got fn, so let's go ahead and draw all the other forces. Okay, there's my mg. Okay, here's the pushing force P. Here's the pulling force T. Now remember, by now you should know an object in contact with a surface, the crate, is in contact with the incline. Fn is the normal force of the incline on the crate. Again, notice that green vector representing Fn is clearly perpendicular to the incline. Okay, so I have Fn. Now remember, the object is sliding down the incline and there's friction. So if the object is sliding down the incline, Fk is directed exactly opposite. Here's Fk. Fk is directed up the incline, right here. That's your Fk. So I've got mg, Fn, P, T, and Fk. Now let's do the components. Well, again, it doesn't matter which way I tilt the incline, whether it's sliding down, tilted down towards the left or tilted down towards the right. That makes no difference. Again, by now, you should all know mg. I know, again, the angle theta of the incline, that's theta. The angle I use to resolve mg, that angle's theta. the angle I used to resolve P, that angle's theta. Now remember, with the tension, that's a different angle. It's a different angle phi. But we don't care because we know phi. All right, so again, by now, mg, the x component is mg sine theta. The y component is mg cosine theta. That never changes. Again, here I'm telling you with this little dotted arrow, that's not a force. That's simply telling you that this component of the pushing force, this component of P, is given by P sine theta. Because again, I know, again, theta, in here, theta. I know this angle right here, theta. That's opposite, so that's P sine theta. The x component of P is P cosine theta. And again, how did I know how to draw it? Remember, I have to go vector P. I have to go from point A to point B. I have to go from here to here. Well, that's achieved by going down the incline and then up in the y direction. Okay, so those are the components of P. The y component is P sine theta. The x component is P cosine theta. Now what about the tension force, the pulling force, the tension force T? Well, the x component, again, the angle phi was given in the problem. That's the angle phi. Remember, it's the angle that the tension force makes with respect to the incline. Clearly, that dotted line right there, that's clearly parallel to the incline. So the x component of the tension force is T cosine phi. The y component of the tension force is T sine phi. Again, how do I know how to draw them? Well, remember, the tension force goes from, a vector goes from point A to point B. So that's achieved by going down and then up. So I'm going in the positive x and then the positive y. So now I've got all my components. Fk. So I've got all my forces, I've got all the components. Now remember, because the object is sliding down the incline, that represents the positive x direction. So let's look at a good figure does the work for you. P cosine theta is positive. Mg sine theta is positive. T cosine phi is positive. Fk is negative. Remember, that's the simplicity of whatever the direction of the motion is along the incline, that's by definition positive x. So again, P cosine theta positive, T cosine phi positive, Mg sine theta positive, Fk negative. Now in the y direction, just as drawn, Fn, T sine phi, and P sine theta, those three are positive. P sine theta, Fn, and T sine phi are positive. Mg cosine theta is negative. Now remember, the speed is constant, meaning that the acceleration is zero. So again, the positives for each direction, the positives must equal the negatives. That's when you apply Newton's second law. Now notice, again, we want the coefficient of kinetic friction. Again, we're not in the business of reinventing the wheel. I know, again, in the box down here, because Fk is equal to mu k Fn, that's always true, no matter what the geometry of the problem states. Because Fk equals mu k Fn, mu k is Fk over Fn. So I need an expression for Fk. Well, clearly, look at your diagram. Fk, the one, it's in the negative x direction, mg sine theta, p cosine theta, t cosine phi, they're in the positive x. Well, remember, a is 0 because the speed is constant, so the positives must equal the negative, i.e., Fk must equal mg sine phi plus p cosine, mg sine theta, excuse me. Fk must equal mg sine theta plus p cosine theta plus t cosine phi. You know, don't let the phi's and the thetas confuse you. Now notice, what is Fn? Well, I know that Fn plus p sine theta plus t sine phi must equal mg cosine theta. In other words, Fn plus p sine theta plus t sine phi, those three positives, you know, this plus this plus this. The three positives must equal the negatives. So Fn plus p sine theta plus t sine phi must equal mg cosine theta. In other words, Fn, because I want to cut right to the chase. I want the fraction Fk over Fn. Well, that means Fn must equal mg cosine theta minus p sine theta minus t sine phi. Very, just make sure you understand why I have those two equations respectively for Fk and Fn. Well, what is mu k? Mu k is simply Fk divided by Fn. So this equation, that equation divided by this equation. So Fk over Fn, mg sine theta plus p cosine theta plus t cosine phi divided by mg cosine theta minus p sine theta minus t sine phi. But it's just Fk divided by Fn, the equation for Fk, divided by the equation for Fn. You know all the values. You know the mass. You know the mass of the crate. You know the angle theta. You know the angle phi. You know P. You know T. Obviously, G is 9.8 meters per second squared. You know M. So you know all the values. Plug it in, and you get a 0.955. Remember, coefficient, no units. But less than 1, that just means, hey, there's a great deal of friction between the crate and the incline. But who cares? As long as it's less than 1, we're fine. So again, if you can understand where this equation for Fk came from and where the equation for Fn came from. Why? Because I want Fk divided by Fn. And that's just applying Newton's second law. This comes about, the Fk equation comes about from applying Newton's second law in the x direction. And the equation for Fn comes about from applying Newton's second law in the y direction. Because again, v equals constant, meaning there's no acceleration. So Fn plus p sine theta plus t sine phi must equal mg cosine theta. Or Fn equals mg cosine theta minus p sine theta minus t sine phi. Likewise, in the x direction, again, a is 0. So the three positive forces, p cosine theta plus mg sine theta plus t cosine phi, must equal Fk. And again, why? Because mu k is always Fk over Fn. Alrighty, let me go ahead and save this video and get it posted.